All right, let's dig into some more detail on what we'll find in an NMR spectrum, a proton NMR spectrum more precisely. And the first thing that we're going to, there's all sorts of details we can find in an NMR spectrum. The first thing we're going to look at is the number of signals. So for example, this spectrum has 1, 2, 3, 4, 5 signals. And what does that tell us about the structure? So this is going to be an indication of how many unique types of protons there are in a given compound. And this textbook reference here, this is section 4. This is for the Klein textbook as chapter 15. So what we're asking is how many unique protons are there in a given compound? So we can label them. We'll do some exercises labeling them. Each unique proton is A or B or C. And then we can also do the same exercise for carbon, the carbons in our structure, because you can also do C13 NMR as well. So, okay, we have 8 hydrogen atoms in this structure. If we're going to analyze propane, we have 8 protons. Does that mean in an NMR we're going to get 8 signals, you know, all spread out along our spectrum? And the answer is no, because certain protons are equivalent. For example, all 3 protons on that methyl group, we can rotate around, they can interchange for each other. There's going to be no way of distinguishing one from the other. They're all going to behave the same in the NMR instrument. And so the way we describe that is we say that all 3 protons are equivalent. They're equivalent in the view of the spectrometer. Okay, and so we can call these type A. Let's call these type A protons. Well, how about this CH2? This CH2 is going to be a unique environment compared to the CH3. So these we will be able to distinguish and will be different. So we can call that type B. But when we come back to this last methyl group, this other CH3, hopefully you can see that this has a plane of symmetry here. So when we have a plane of symmetry reflecting one set of protons onto another set of protons, that's going to make them equivalent in the NMR as well. So these are going to be type A as well. Okay, so and for propane, there are 8 protons, but there's only 2 signals. There's going to be 2 signals in the NMR. We can call them A and B. And contributing to signal A, we have a total of 6 protons, right? We have 6 protons of type A, and we only have 2 protons of type B. So the ratio of those 2 signals in the NMR is going to be 3 to 1. This, by the way, is described as the peak integration, which is another feature that we can observe from the NMR. We'll talk about that in another lecture. So we'll get 2 signals, and we'll find that the signal A is 3 times the area of signal B, because it has 3 times as many protons as the CH2. All right, how about our next one? Let's take a look at this. We have, and in fact, if you want to maybe pause this to try this on your own, this is a great chance to see if you can do some of this analysis. And when you're ready, you can come back and we can work through this together. Okay, so how about this CH3? This CH3, once again, all 3 protons, we can rotate around that and exchange those, interchange those. So those will be type A, and there's 3 hydrogens of that kind. And then the next one's this CH2 is unique, and we'll have 2 hydrogens of type B. And then how about the next CH2? Do you think it's going to be the same as the first CH2? Well, no, because this one is right next to a benzene ring, while this one is right next to an oxygen. And so those are unique. And so that will be type C. That will be type C. Let me write that a little more clearly. Okay, are there any other protons in the structure? Yes, there's on the benzene ring. We call it a benzene ring when we have a 6-membered ring with alternating pi bonds. That is actually kind of a very unique functional group that's going to be important to us in the NMR. And so that has 5 protons on it. But we're not going to expect 5 unique signals, because once again, this this part of the molecule has some symmetry. And so the two, the one hydrogen that is opposite is one kind, but the two that are right next to the carbon substituent here, those are going to be equivalent. So if we call this proton type D, this is also proton type D. This next one will be type E. There's 2 protons of type E, and this last one that's all the way across from the substituent is on its own. There's only 1 proton of type F. Okay, now an interesting little substitution. We can have a little test here, and we'll talk about this in just a minute. But if you're ever not quite sure if 2 protons are going to be equivalent or not, what you could do is you can imagine if I put a chlorine here instead of a hydrogen. If I put a chlorine here, would that be the same compound, or would that be a different compound than if I put a chlorine here? And so because those would lead to different compounds, that's for sure how we would know that they're not equivalent. They're not equivalent. Okay, where if we exchange these 2 chlorines, either of these 2 hydrogens with the chlorine, we'll look at the relationship there too. So that's called a little substitution test. We'll look at more closely at some examples in just a minute. Actually, this is the better example to discuss the substitution test. Okay, so if we look at the alkene over here, the carbon-carbon double bond, we see that there's 3 hydrogens here. There's 3 protons. And this is where if you had a chlorine, if you put a chlorine at this position, it would be a different molecule than if you put the chlorine at this position, because we don't have rotation around a carbon-carbon double bond. So even though this is a CH2 and they're both on the same carbon, they're actually not equivalent. So it's possible to have protons on the same attached to the same carbon that are not equivalent. So this will be proton type A, this will be proton type B. And those 2 will be different from proton type C. Okay, down here we have a CH3. All 3 protons on a methyl group are always equivalent. So we could call those type D. There's no protons here, right? Remember, carbon always has 4 bonds, so we can use that to interpret, identify where we have protons on a line drawing. Which means on this carbon we do have a proton, right? Because I see just 3 bonds, so there must be a 4th bond here to hydrogen. So there's a proton here. This is type E, and this is a CH as well. And so that is type F. Okay, and then we have these 2 methyl groups. These 2 CH3s. The question is there any way that these 2 methyl groups can be would be identical? And yes, they would, because we can rotate to exchange each of those. And so both of those, all 6 of these protons will occur as a single signal. Okay, now sometimes when we say that protons are equivalent in the NMR, it's because that little substitution test gives us the exact same compound. Other times that substitution test doesn't give the exact same compound, but gives enantiomers instead. And so let's take a look at this structure when we really think about the stereochemistry of the different of the protons on a given CH2, for example. And we consider this wedged proton compared to this dashed proton, would say, well, actually, these are in different again, even though it's a CH2, these are in different environments, right? This proton is cis to the t butyl group. This one is trans to the t butyl group. They're not going to be equivalent. Okay, so let's start one by one. Let's just start one by one. This bottom proton, there's no other proton like this one. That's a CH. That's on the same carbon as this t butyl group. So that would just be type A. But now when we move on to this next CH2, the whatever one is on a wedge is going to be different than the one that's on a dash. One is cis to the t butyl group, one is trans to the t butyl group. Okay, now we describe these two protons as being diastereotopic. Diastereotopic, meaning they're different in the NMR. They're unique in the NMR. They're non-equivalent in the NMR, I should say. Let's use that. That's a more precise term. Sorry, non-equivalent. Okay, why do we call them diastereotopic? It's because when we do this replacement test, if you imagine putting a chlorine here or a chlorine here, what's the relationship of those two compounds? They they have the same connectivity, but they only differ by their spatial arrangement. And the two compounds we would make are diastereomers. So those protons are described as diastereotopic. And what we could say is that replacement with, we could just say X. Okay, again, I like to use a chlorine atom, for example, with something, gives diastereomers, results in diastereomers. Sorry, my handwriting is tough today. Gives diastereomers. So two protons that would result in diastereomers, a pair of diastereomers with the replacement test, are described as being diastereotopic. Okay, and those are not equivalent in the NMR, which means they're going to have different delta values. Are going to be at different ppms. They are going to have different J values with their neighbors. They're going to have different splitting. Some might be, a tiny doublet. One might be a wider doublet, for example. And they can split each other because they consider each other neighbors. So when we have something like this with diastereotopic protons, the NMR all of a sudden becomes very, very complex. Okay, so let's continue looking at the next CH2. The next CH2 is different from this CH2, but again, the relationship to each other is diastereotopic. So we would call this D and E. We could call that D and E. And then the two on the very opposite end of the ring are also are different from the other CH2s, but they are also different from each other. So we could call that protons F and G. Okay, now what happens when we move to the other side of the ring? All of a sudden we do have a symmetry element. And I said, when you have any protons that can be are related by a plane of symmetry, they're going to be equivalent in the NMR. They're not going to be different in the NMR, which means this wedged proton is D. So over here, this wedged proton is also D. And the dash proton is going to be E. Now, are they really, if I did that replacement test, and I put a chlorine here, or I put a chlorine here, would I get the exact same compound? I would not get the exact same compound. If you draw those out, this compound or this compound, and compare the two, you would see that they are actually mirror images of each other. They are non-superimposable mirror images. We call those enantiomers. So if the replacement test leads to a pair of enantiomers, what we describe, we will describe those protons. Let's see if I can use a different ink so it doesn't clutter this too much. We describe these protons as being enantiotopic. Enantiotopic. And but in an NMR, they are indistinguishable. Okay, so they are equivalent. They are the same in the NMR. So we're going to label them as the same proton type. We don't expect them to occur at the exact same place on the spectrum. All right, so what does it mean to be enantiotopic? Enantiotopic means that replacement with X or whatever, whatever group you want to use for your replacement test gives enantiomers, gives rise to a pair of enantiomers, meaning mirror image relationship. And these, you could see, have the exact same chemical shift, exact same splitting with, interaction with its neighbors and so on. Okay, and what do we call just plain old things like on this methyl group, on this CH3 group, those protons that all come together, there's no distinction if you did the replacement test and the two resulting structures are identical compounds. That's what those would then be called homotopic protons. So the replacement with X gives the same compound, same exact compound. And so indistinguishable by the NMR. So for example, the protons on a CH3 group, would always be described as homotopic protons. So just an FYI, this might not be something that your instructor emphasizes or requires you to be able to distinguish. But this term diastereotopic is a pretty important one because it explains why sometimes the two protons on a CH2 are not equivalent. And it's typically because we are near a chiral center, or something that would be a chiral center if we did this replacement test. All right. Okay, but when it comes to identifying the different types of protons, we could simply think about rotation around a bond. If that will swap them out, we know they're going to be equivalent. Or if there's a plane of symmetry reflecting them, that makes them equivalent. Okay, the reason E and D are non-equivalent is there is no plane of symmetry that reflects them, right? The plane of the molecule of this ring is not a plane of symmetry because it would reflect the 2-butyl group onto a hydrogen. So so that's why they're non-equivalent. Okay, our last CH2 here, what are they going to be? How are they going to be described? The wedged proton is type B, another type B, and the dash proton is type C. Very good. Do we have any other protons here? How about the T-butyl group? We actually have 9 protons here. There are 9 protons on those 3 methyl groups, and those are all the same type. So where are we? A, B, C, D, F, G. This would be type H. Excellent. Okay. While we're here, let's take a look at our peak integration. The peak integration. And that is because we talked a little bit about that ratio, right, of having the 3-to-1 of types A and type B. Sometimes the peak integration very simply is provided with each signal. It says, okay, there's 6 hydrogens contributing to this signal, 3 for this, and 1 for this, and 4 for this. Okay, so so that is very nice when that happens. So sometimes sometimes it's simply given as the number of protons. So these values are indicating the integration, the number of hydrogen atoms, the protons that are contributing to each peak. Okay, other times though, instead of giving you the number, it just gives you the actual area under the peaks that was calculated by the spectrometers, by the software. So that is we have to learn how to interpret those numbers. We'll get some practice doing that. So the area here, this is 25 and 25 and 24 and 38. Okay, so what we have to do is we have to figure out what is the ratio of those numbers? What is the ratio of those numbers? So sometimes this is another option. Sometimes these integral values are the area under the peaks is given. So instead of just telling you the ratio and telling you the number of hydrogens, the area simply is given, and then you have to calculate the ratios. Calculate or determine the ratios. Okay, so so when we take a quick look here, you know, 24, 24, 24, and 36, that would be like if every proton was if one hydrogen was around 12 units of area, then we would see that the ratio here is that this is 2, and this is 2, and this is 2, and this is 3. Right, this number is 50% bigger than the others. So from that, then we could on our own determine that these two peaks around 7 and 6.5 are correspond to 2 hydrogens, 2 protons. The one here is 2 protons, and this last one is 3 protons. So we want to get some practice in working with the with these ratios if we're given those instead of the discrete numbers. Okay, so that that wraps up how we can predict how many protons, how many unique types of protons there are, and therefore how many signals will be in an NMR. And we can also use that to determine what the integration of the peaks will be as well. In other words, how big are they? How large are they? And the more protons of a certain type, the larger that peak is going to be. Okay, now we can't visually tell because every peak has a different shape, right? So this is a singlet, so it, you know, and this is a doublet, and we're comparing apples to oranges. So that's why we need the computer to calculate the area under those peaks and give us the actual number, and we can use that to determine a ratio.